following definition of a measurable map. Or mapping, I don't know, mapping, it says in the book. So we start with two measurable spaces. So these are sets equipped with sigma algebras, and we take a map T from one into the other one, and this one is called A prime measurable. If, and the condition is the pre-image by T of a measurable set in A prime, so a set in A prime should belong to the sigma algebra A for all A prime in A prime. Yeah, so we saw a picture, don't know if it's any better than the writing, but I'll draw it again. So if this is X equipped with the sigma algebra A, and I have my map T, that takes me to the set X prime equipped with the sigma algebra A prime. So the fact that T is measurable means whenever we take A prime, but this A prime from the sigma algebra A prime, and I look at its pre-image by means of T, right, inside X, so this is T inverse of A. The requirement is that this should be in A. Yeah, so the pre-images of sets in the sigma algebra here should be taken to be in the sigma algebra on X. Okay, and then we have a short way of writing this. So instead of this, we can say, for short, we say that T inverse of A prime should be contained in A. That's the same way, same thing as writing this. The book has a preference for this one, so I hope we all understand what it means. Okay. So this is the definition of a measurable map. And maybe there is another piece of notation that we should put down so that you can see what it means. In the case when the measurable space that you start with comes equipped with a measure, moreover with a probability measure. So, you know, it's a measure such that the size of the total set is 1. So in this case we say this triplet consisting of a set, a sigma algebra on it, and a probability measure is a probability space. And T is a map from X into another set X prime. X prime is just a measurable space, so I only have a sigma algebra on it. So and T is like that, and T is A prime measurable. We say, or we refer to T as a random variable. So lots of words in here. What I mean with this is, if I have a measurable map between two measurable spaces and the first one happens to be a probability space, so it has a probability measure on it, then such a measurable map is called random variable. And this you will encounter a lot in, well, you will encounter this a lot in block 2, 2, this notion, if you wish, and you work with it. But it's just nothing but a measurable map between measurable spaces, the first one being a probability one. So it's just random variable. I think perhaps maybe in block 2 you would call this stochastic variable, but it's the same thing. So I want to give you some examples, very simple examples. The book seems to overview them, but I think it's instructive for us to just understand this notion and look at some very simple examples. The first one that I bring to you, it's the one of constant maps. So what I mean by this, it's the following. I have 2 measurable spaces. So sets equipped with sigma algebras, A and A prime. And you take B to be a point in X prime in the target space and define T from X to X prime by letting everything go to B. So that's for all X and X. So this map takes everything to this special point B in X prime. And then the claim is that T is a prime measurable. So this is a slash, A vertical slash bar, A prime. Okay, so let's do it. We'll just do it by definition. Right now we don't know very much. We only know what's the definition of a measurable map. So I would say true, although it's very simple. So we have to take an arbitrary set A prime from the target sigma algebra, A prime, and we have to show am I playing with the slides? Yes, sorry. We have to show that T inverse of A prime belongs to A. So you see, what matters here is that the image is this special point B. So we have 2 cases. Yes, that's good. Sorry, I turned them all down. I'm sorry. So we have 2 cases. In the first case is when the set A prime contains B, and the second is when A prime does not contain B. So if B belongs to the set A prime, can you tell me anything about the pre-image of the set A prime? Can I say exactly what it is? Some people say yes. I would like to hear what is the pre-image of A prime. What are all the points in X that will go into the set A prime? A prime contains the point B, and everything goes to B. So, yes? It's all of X, exactly. Is this in the sigma algebra A? Yes, because A is a sigma algebra on X. In the case when B is not in an A prime, then what's the pre-image of the set A prime? Yes? It's the empty set. There is nothing that goes into the set A prime because everything goes to B, which is outside A prime. It's the empty set in the sigma algebra A? Yes, because A is a sigma algebra on X. So you see, in either one of the cases, and there is nothing left, we have this and we are done. Okay? Very simple example, but sometimes you need to start with simple ones and move on to more complicated. Okay, so another very simple example is the one of the identity map. So that means that I'm only looking at one measurable space, and I'm looking at the map T, which takes X into X, defined take a set A prime in A. Now, which A is that? It's the A in here or it's the A in here? First or second? Yes? Second. So maybe I'll make it like this. I'll take, so it's the sigma algebra on the image space. So let A prime in A to show that T inverse of A prime belongs to A, and that's the sigma algebra on the domain space. Okay, is this true? What is the pre-image of the set A prime by means of this map? What are the points in X that go to the set A prime? Yes? A prime. So that's the whole point here, that this thing is equal to A prime, and of course A prime is in A because I took it from A. So, if it looks silly, it's because it's very simple, but you have to work with the definition, and that's all we have, the definition. So these are two very simple examples of measurable maps, and maybe let's now move to some more interesting ones. So my next example is something that should look familiar. We talked about it last time. So fix a point X in Rn, and let's consider the map tau sub X, which is defined in Rn, on which I take its Borel sigma algebra and goes into Rn, on which I take its Borel sigma algebra, and I define it like this: tau X on a vector Y in Rn is Y plus X, all Y in Rn. So this is a map which translates every vector by X. So if you want to have a picture, let's do it, say, on the blackboard, so in R2. If this is my fixed vector X to begin with, maybe I'll make it blue. So this is fixed. If I take another vector Y in Rn, say here, do you know how you write Y plus X? So you have to take where Y ends, and then you move it right in the direction of the vector X, like this. So then you close this parallelogram. Yeah. This is the Y plus X. Right, so what this map does, it takes any vector and translates it by X. So I'm going to end up here. Right? Okay, so what I would like to ask is this map tau X B over N measurable? You have an answer already? Maybe I write something and then we can talk about it. The answer is yes, but let's see why that is the case. So let B, call it B, in the Borel sigma algebra of Rn in here, so B in here. I want to show that the pre-image of B by means of this translation map is a Borel set in Rn, right? That would be by definition giving that this map is measurable. So let's look at this. The pre-image of the set B by means of the map tau X, this will be all the vector Y in Rn such that tau X of Y belongs to B. Right? That's the definition of the pre-image. But this is the same as all Y in Rn such that the tau X on Y is Y plus X. Right? So these are all the vectors in Rn such that when you add X to them, you land in V. That's the same thing as you would agree if I write understand this notation? A set minus a point. That means all vectors of the form y minus x, where y belongs to b, or z minus x, where z belongs to b. Yeah? This is a notation. So this means all z in Rn. Okay, let's put it like this. All elements of the form z minus x, where z belongs to b. It's a set, right? So it consists of differences between elements in b and x itself. Right? So it's elements of the form z minus x, where z belongs to b. Because when you add x, you get value to b. Okay, so can we decide whether this is a Borel set in Rn or not? Question mark. So I started with the Borel set. I'm translating it by minus x. I'm asking you, is this a Borel set or not? Do we know it? And now you can tell me.
Yes, we showed last time that Borel set is
The collection of Borel sets is stable under translation. So last time I showed with the b plus x, but now you replace it. It was true for every vector, so now you take it for minus x. So the answer is yes. We saw last time. Okay, so that's what's responsible for this. But now maybe we want to give a different solution to this. So a different solution. And here is what I propose to you, much along the lines of how we showed last time that a translation of a Borel set is Borel. Let's check it on special sets. So I'm back to here. So I start again from this. So this is my starting point. I have a Borel set in Rn. I want to show that the free image is Borel. So let's look at a specific collection of Borel subsets of Rn, namely the familiar boxes. Right, so this belongs to this collection Jn, which is a part of the Borel set. So I'm interested in what's the pre-image of such a box. A1, B1, An, Bn. Can you tell me what's the pre-image of a box by means of this translation map? So you may want to write your x using these coordinates. Yes?
It's also a box, it's just like A1 minus x1.
A1 minus x1, B1 minus x1 times, I hope I can squeeze it, An minus
xn.
yes, and Bn minus xn. Yes, that's right. So this is a box. So this is again in Jn, which is part of Rn. Yeah? So I can show that this condition here is satisfied on this special class of Borel-Sigma or of Borel sets in Rn, namely the boxes. So the question is, can I conclude from this that tau x is ERN measurable? So just knowing that this property, pre-images of Borel sets is Borel for a special class of Borel sets, can this allow me to conclude it's true for all? And the answer is yes. See next lemma. So I wanted to point out to you why this next lemma is so important, because it allows you to check that condition in the definition just on a subclass of sets. So this is lemma 7.2 in the book. So you start with 2 measurable spaces. And you have, maybe I write it in some sort of color, you have a sub-collection of the sigma algebra A prime, but such that the sigma algebra that this G prime generates is equal to A prime. Yeah? So in the previous example, we have our A to be the Borel sigma algebra of Rn. We have our A prime to be the Borel sigma algebra of Rn. And what is this G prime? G prime is Jn, right? The collection of boxes. So this one sits in A prime, and the sigma algebra that G prime generates is A prime. The whole Borel sigma algebra of Rn, right? Okay, so this is how you should think of this theorem if you want a very concrete interpretation. And then I have a map T. So then T from X to X prime is A prime measurable if and only if the condition is that the pre-image of sets in G prime land back in A for all G prime in G prime. So I hope that it's clear what's the meaning of this lemma. So it allows you to check the definition condition of measurability on a subclass of or subcollection of A prime. It's a subcollection with the property that it generates the whole A prime. Yeah, and the example here tells you that if you think of this subclass as being one that generates the Borel sigma algebra, so in particular in that case the collection of boxes, then it's enough to check this kind of thing on boxes in order to deduce it for the whole Borel sigma algebra. Okay, so that's the statement. So again, such a thing for short, we can also write it as T inverse of G prime is contained in A. Yeah, it's the same thing as writing that. And I think, again, the book has a preference for writing this most of the time. So this is an if and only if statement, so that means we have to prove 2 implications. So let's prove this one. So suppose T is A prime measurable. We have to show that T prime of G prime, so if G prime is a set in this collection G prime, then T inverse of G prime lands in A. Is this true? I know that my map is measurable. I take a set in G prime, right? This is what I have to show. The pre-image of everything in G prime lands back in A. It's not a deep question, so don't think too complicated. Why would this be true? Yes?
Because it's A prime.
Exactly, and you tell me exactly what I have to write. I have to write that G prime is a part of A prime, right? Exactly. So this is true by definition, since G prime belongs to G prime, which is contained in A prime. right? That's what I have to write. So there is not much to prove about this. However, the other implication, there is some content to it. So suppose I'll repeat T inverse of G prime belongs to A for all G prime in G prime. What we want is T is AA prime measurable, that is T inverse of A prime belongs to A for all A prime in A prime. So A prime is a larger collection, right? Just by knowing that this property is satisfied on a smaller class in A prime, I want to deduce it that it holds for all. And you can think about it, and maybe you guess how to be done or not. There is a specific trick that will be used a lot in this area that we are talking about. So here is how you do it. Set. Let's look at all the sets for which such a property holds. So and I'll try to follow the notation in the book. Let me see. All A prime in A prime such that T inverse of A prime belongs to A. So these are the sets I'm interested in, right? Can I say anything about this collection? What I would like to know if it is equal to A prime or not, right? The sigma algebra of A prime. This is what I want. Because if I prove this, then I'm done. So how can I obtain that? Do I know anything that belongs to sigma prime? Yes? G prime is contained in sigma prime, yes? That is by assumption. That is our assumption, right? This one, T inverse of everything in G prime belongs to A, right? So by assumption I know this. And let's just see, what would this right now it doesn't imply anything. And, so maybe I tell you, the key point here is that sigma prime is a sigma algebra on X prime. And this you should check, that it is a sigma algebra. And what it really comes down to, its properties of pre-images of functions, the fact that they behave very well with unions, countable unions, and so on, things like that. So I would just say, in pink, you should check this. This is a nice exercise for you to try. So supposing now that we know these two pieces of things, the fact that it contains G prime and it is a sigma algebra. Can you tell me what can I say further out of this? I have a sigma algebra that contains a collection. Yes? Exactly. So then the sigma algebra generated by G prime is contained in sigma prime. So remember, the sigma algebra generated by a collection of sets is the smallest sigma algebra that contains this collection. So here I have a sigma algebra that contains the collection. Therefore, it will contain the smallest one. This is the smallest. So I'm not saying this very often, but for the beginning you need to remember. So this is the smallest sigma algebra containing G prime. Okay, and how do I continue? Exactly, so this whole thing is equal to A prime. And what's the relation of sigma prime to A prime? It's a part of it, right? So sigma prime, it's contained in A prime. So here I have A prime equals to this, contained in sigma prime, contained in A prime, so then that means that they are all equal. Sigma prime equals A prime, and we are done. This is a typical example of an argument that you would give in this part of the course. Yeah, so you collect all the sets that have the property you are looking for, you try to relate to the information that's given you, so this one contains G prime, and then you really want this to be a sigma algebra, and once it is, then the whole thing comes about. Okay? So this result, again, tells you that in order to check the measurability condition from the definition, it's enough to restrict yourself to a sub-collection with a property that it generates the whole sigma algebra. So in the particular case of the Borel sigma algebra, you could check it on boxes, you could check it on open sets or other things. And perhaps, let's see another application of the lemma right away. Continuous map T from Rn with its Borel sigma algebra into, can be a different dimension, Rm with its Borel sigma algebra is measurable. Is Rm measurable? So every continuous map is measurable. Okay? So let's see. Now comes a little bit of analysis 1. T is continuous if and only if for every U open set in Rm, its pre-image we have that, I write it here, T inverse of U, it's open in Rm. Do we all remember this? The characterization of continuity? So it's not correct to say that the map is continuous if it takes open sets to open sets. That doesn't make it continuous, that makes it open. Continuity means pre-images of open sets are open. So now, can we use this information to conclude that the map is measurable? Using that lemma. So maybe I can get some help from one of you, or maybe too much to ask for. Maybe I continue a little bit. Okay, so if T inverse of U is open in Rn, so this means that for every U belonging to, remember we denoted by On, this is the open sets in, or UM rather, OM in Rm, right? We have that T inverse of U is open in Rn, but that is part of the Borel sigma algebra of Rn. Right? So I can check that three images, so forget now this intermediate term, I'm really looking at this belongs to this. So I can show that three images are Borel in the initial sigma algebra, but only for sets which are in this collection of open sets in Rn. Is this enough to conclude that it holds for all Borel sets? And you'd like to look at the statement of the lemma. So I'm checking everything, the lemma up there on the blackboard on top. I'm checking everything for a specific sub-collection of the Borel sets. Yes?
Since the open sets generate.
Exactly. So since the sigma algebra generated by the Borel sets in Rn is the Borel sigma algebra by lemma 7.2, we are done. Yes? now let me write down some examples of continuous maps that we can get to be measurable right away using this. See? So, hence, the following maps are measurable, and we will look at what kind from where to where. So the first map is the one that takes point xy in R2 and maps it to x plus y in R. This is a continuous map, right? So therefore this will be measurable BR2, BR, right? For example, another one would be this being mapped to the maximum between x and y. Or maybe I put a parenthesis here like this. This is also a continuous map, therefore measurable, or x comma y in R2 is mapped to the minimum between x and y, or xy in R2 is mapped to x times y, and so on, etc. You can write down whatever thing that comes to mind, as long as it's continuous. So these are all continuous maps. So the following, I will put it here, continuous maps are measurable. Okay, but of course one has to say there are, however, measurable maps which are not continuous, and that's important. So for example, I'll write down the one that's in the book. X maps to indicator function of the interval -1, 1 at x. So this is measurable, but not continuous. I think that you believe that this is not continuous. You can see it, right? So it has this continuity at -1 and at 1. The fact that it's measurable, I would like to say this is something that it's actually proved in the book in the next chapter. So we'll talk about it next week. I mean, it's not that you cannot do it today. You can absolutely do it today, but for some reason then he talks about it in the next chapter, where he considers mappings that go specifically into the real line, such as this one. And he proves it in there. So it's very important that there are measurable maps which are not continuous, because remember, we want to construct a theory that it's larger than the theory of Riemann integrals, and we could integrate all continuous functions. So if we don't have more functions than the continuous ones to work with, that means we're not doing anything any better than what we did before. So there are plenty of measure maps which are not continuous, and this is the point of Lebesgue integral, to learn how to integrate these maps and work with them. Okay, so I think that we have 5 minutes, and I would like to write down another result. It doesn't take long to write it. It's about composition of measurable maps. It will basically be a picture. So this is theorem 7.4 in the book. Composition of measurable mappings. Okay, so why don't I just make the picture instead of writing the statement? So the picture is this. I have a measurable space called x1 equipped with a sigma algebra A1. I have another one called x2 with a sigma algebra A2, and I have a third one, so I need to erase further. Maybe T goes from x1 into x2, and S goes from x2 into x3. And I know, moreover, that they are measurable with respect to the corresponding sigma algebras. So this one is A1, A2 measurable, and S is A2, A3 measurable. Once you have two maps, maybe I'll make my T in yellow because I wrote about it in yellow. And then I have the other map S, like this. Once you have two maps like this, you may get tempted to compose them. I don't mind it. I give up. I don't give up. So you compose them and you get a map that goes from x1 into x3, and that is it T composed with S or S composed with T? Yes? S composed with T because T goes first, right? S composed with T, this is this map. So then the conclusion is that S composed with T, which goes from x1 into x3, is A1, A3 measurable. Yeah, so the composition of the measurable map is measurable. So let's see the proof. It will be done on the picture. So to prove that something is measurable, you have to show that whenever you take something from the sigma algebra A3, the pre-image by S composed with T will be in the sigma algebra A1. So let me take a set here. This is A3 from the sigma algebra A sub 3. Maybe I make it smaller like this. So this one, A3, belongs to A3. And I act on it with the map S. So it gets moved here, as inverse rather. It gets moved here to a yellow set. So this is A2. And this A2 is going to be S inverse of A3. Yeah. And now this one is being taken here by T inverse, and it will be brought to A1. And this A1 is, what do I write it so you can see it? A1 is T inverse of S inverse of A3. Right? Because here you act with T inverse. So this becomes T inverse of S inverse of A3. That's A1. Okay? So now let's see about that measurability. So I know that this doesn't look good. It looks like a straight A and it should be a calligraphic one. So I know that this is from A3. Where is this A2? So A2 is S inverse of A3. S is a measurable map, A2, A3. So if I have a set from the sigma algebra A3, then this one, I lost my yellow, it's going to land in A2, right? And now I'm taking something from